So, we continue with our discussion on logic design. This is the third part of our logic design lecture. Now, here the first thing that I would like to talk about is to discuss some kind of special decoder design, but before I go into it, let me try to give the motivation. See, we talked about the design of decoders. Now, you imagine that you are trying to design a 4 to 16 decoder. Now, if you design 4 to 16 decoder directly using gates, not using smaller decoders as we had seen, directly using gates, then for every output you need a large gate, you need an AND gate with 5 inputs. 4 inputs will be some combination of the input variables and 1 for the enable. So, you will be needing 16 AND gates, each with 5 inputs. Now, one difficulty in designing circuits is that when the number of inputs of a gate increases, it becomes increasingly difficult to design and manufacture those gates. Well, the gates become unreliable, they consume more power, they become slower, and there are many drawbacks. So, it is always attempted to keep the number of inputs to a gate as small as possible. So, instead of designing a very large decoder just in one go, it is always better to design smaller decoders and use it to build a big decoder, larger decoder. Like the example we showed, that using 2 to 4 decoder we can construct a 4 to 16 decoder. Now, here we show an alternate approach. Here also we are trying to build a 4 to 16 decoder, but the approach is different. So, here I am showing the schematic. So, we are using 2 to 4 decoders. So, the concept is that I am using a row column concept. There are 4 columns and there are 4 rows. One of the decoder, depending on 2 of its inputs, will be selecting one of the rows. The other decoder, depending on the other 2 inputs, will be selecting one of the columns. Suppose you apply W x equal to 1 1, which means the 4th row is selected, and if you apply W z equal to 1 0, which means 3rd row is selected. So, it is 1 1 and 1 0. So, this last row and 3rd column means I am referring to this junction. Now, what I do, at every junction I connect an AND gate. You see, every row line and every column line I connect as inputs to an AND gate, and the output of the AND gate are my decoder outputs. So, just to imagine here 1 1 and 1 0 will what? If it is 1 1, then only the last row will be 1. If it is 1 0, the 3rd column will be 1. Now, if I connect through these 2 lines an AND gate, both of these inputs will be 1 and 1. I have connected this and this. So, the output will also be 1, but for all other AND gates, these both inputs will never be 1, at least one of them will be 0. So, all others will be 0, only this will be 1. So, this works perfectly as a decoder. Depending on what I am applying to the input W x and Y z, exactly one of the gate outputs is becoming 1, that is my decoder output. Okay. Normally, large decoders are built or constructed using this way, because here as you can see, the number of gate inputs are all small, all 2 input AND gates you require, right. Okay. So, let us move on. So, let us talk about another kind of a special decoder, which is sometimes very useful, particularly when we work with BCD numbers. We need to use a decoder to identify what decimal digit or BCD digit is that. We need a decoder which is called a BCD to decimal decoder. BCD, as you know, a BCD is a 4-bit number encoding, let us say W x y z is a BCD, and in a BCD number the valid numbers go from 0 0 0 up to 9. The remaining 6 combinations are considered to be not valid. So, in the output we have only 10 outputs, not 16 outputs like in a normal decoder. Depending on whether you are applying one of these, so one of the outputs will be 1. So, again there is an enable. So, the way you construct the decoder is exactly same as a normal decoder. Let us say this 5, the gate for this 5, what this 5 indicate? 5 is 0 1 0 1. So, you will be connecting, you see, first one you connect enable, then you connect x, then you connect y bar, then you connect z, and of course, w bar. So, this way you can connect these inputs in various way, and of course, here what final realization we have shown is after minimization, because you see in this case among the inputs there are 9 valid inputs and there are 6 do not cares. So, when you do a minimization, these do not care inputs also will result in the cancellation of some of the terms. So, I am showing just the final realization, okay? I am not showing you the steps of minimization. So, this is another kind of a decoder that we use in some designs, BCD to decimal decoder. There is another kind of a decoder which is also very useful. Well, we have also we have all seen this kind of digital displays in many gadgets and places, in our calculators, in our washing machines, in our refrigerators, different places where there are some digital displays. The numbers are displayed in a very specific way. These are called 7 segment displays. So, how the 7 segment display? You see here I have shown a picture of a typical 7 segment display unit. You see in a 7 segment display unit there are 7 lamps which are typically numbered or named as A, B, C, D, E, F, G. By selectively glowing these lamps, you can display any of the digits from 0 to 9. Let us say if you want to display 5, you display these digits, these lamps, this is 5. So, if you want to display 3, you display these. Okay, so, 0 to 9 you can display anything, right. So, basically the 7 segment display units that we talk about, these displays, there are 7 display segments that I have shown here. And the way they are manufactured, that can be different. They can be manufactured using light emitting diodes, liquid crystal displays, neon lamp or any other technology. So, as I had said the examples, depending on what digit you want to display, the appropriate segments should be activated and they should glow. Okay. So, these displays come in 2 variety. Let us talk about light emitting diode LED kind of displays. The first variety is the common cathode variety, where these 7 segments are actually 7 LEDs or light emitting diodes. They are called common cathode because as the cathode terminals of the 7 LEDs are tied together, this is the common terminal which you connect to ground, and you apply a voltage to this ABCD FGH input depending on which one you want to glow. Okay. Similarly, you can have a common anode kind of a display unit where the LEDs are connected in reverse order. The anode point is connected together and they are connected to a positive supply voltage. and when you want to glow a digit, you will have to ground the corresponding input, so that a current flows. Okay. Now, in the example that we will be showing, we will be assuming that it is common cathode. That means, if you want to display a segment, you have to apply a high voltage, let us say 1 on that line, the other side is grounded. So, when you talk about BCD to 7 segment decoder, we are talking about a circuit like this. So, we want to design a decoder like this, where there will be 4 inputs applied. This is our BCD input, and 7 segment outputs will be generated, which will be connected to the 7 segments of this display A, B, C, D, E, F, G, and depending on the BCD input, the correct segments will be activated, so that the corresponding digit glows. Okay. This is the basic idea. So, the truth table for the BCD to 7 segment decoder looks like this. So, I have also shown a 7 segment display here side by side for reference. Let us say my digit is 0. So, when I want to display 0, other than G, all the other segments should glow. So, you see A, B, C, D, E, F are all 1, only G is 0. So, if I want to display 1, only B and C must glow, all others should be 0. You see, only B and C are 1. For 2, A, B, G, E and C should glow, F and C should be off. You see, for 2, C is off and F is off. So, like this you can display all the digits. Say for 8, all the segments should glow, all are 1. For 9, only E and D should be off. For 9, only E and D should be off, others should glow. So, it is easy to construct this table, right, corresponding to the BCD input code. So, exactly how I want to display it. So, you can just activate the segments, assuming common cathode display, that 1 means it will glow, 0 means it will not glow. Okay. And just from this you can write down the expressions also. I have not shown you the exact process of minimization again. Well, I leave this as an exercise for you. This is a 4 variable function. There are so many do not care states, 10, 11, 12, 13, 14, 15. There are 6 do not care states. So, when you use a Carnot map, you can use these do not care states also for minimization. Let me take one example as an instance. Sorry. Yeah. Let us take one example. Let us consider a 4 variable Carnot map. Let me show you one. X1, X2, X3, X4, let us say X1, X2 is in this direction, X1, X2 and X3, X4 in this direction, let us say. So, the inputs are 0, 0, 0, 1, 1, 1, 1, 0 and 0, 0, 0, 1, 1, 1, 1, 0. Let us take the segment A for example. Okay, segment has many more, let us take another, let us say segment C. C can be minimized, let us say C. Look at the segment C, or fine, A is fine, let us take A. Look at the segment A. So, you see where they are 1 for 0, this is 0, 1, 2, 2 is 0, 1, 2 is this, then 3, 3 is also 1, this is 3, 4 is 0, 5, this is 4, this is 5, 5, 6, 7, 4, 5, 6, 7, this is 7 and 8 and 9, this is 8 and this is 9. This is your Carnot map, and in addition there are 6 do not cares 10, 11, 12, 13, 14, 15. 10 is 1 0. So, I am showing the do not care as x, these are all do not cares. these 6 are do not cares. So, now you will have to just include these ones and go ahead with the minimization. So, you can make the cubes like here the 4 corners will be a cube, then you can have a cube like this, you can have a cube like this, you can have a cube like this, you can have a cube like this. Like this, if you do a minimization, you will be arriving at these expressions. Okay. I am not working out all of them, I leave it as an exercise for you. So, you can actually verify this. Okay. Minimize this and see that whether these expressions are tallying with this. Okay. Let us move on. Next, let us come to a circuit which you can call it is an reverse of the decoder. I call it an encoder. There are many inputs, there are few outputs. Depending on which input is activated, at a time I am assuming only one of the input is active. So, the output will contain the binary code of the input, which input that is active. Let us see how it works. So, an encoder will typically have 2 to the power n input lines and n output lines. So, here there is an example for n equal to 3. There are 8 input lines and 3 output lines. So, I am assuming here that only one of the input lines is 1 at a time. Let us say D 3 is 1. The output will contain the binary code of D 3. 3 is 3. So, it is 0, 1, 1, that is 3. This will be the output. If D 6 is 1, 6 is 1, 1, 0. So, it will be 1, 1, 0 and so on. This is how the encoder will work. So, for a normal encoder, the truth table will look like this. So, in the first case I am if you see here again you need not show all the there are 8 inputs. So, there will be 2 to the power 8 possible input combinations. So, you need not show the whole truth table, because this is a functional block, you can show only the functional rows. The first row says only D 0 is 1, others are all zeros. So, this will mean 0 0 0. If D 1 is 1, 0 0 1, D 2 is 1, 0 1 0, like this, because the other inputs are not valid, they are all do not cares. Okay. Now one issue here is that in this kind of an encoder design, that you are assuming that exactly one of the input is at 1, but let us say by accident or otherwise I have also made another input as 1, let us say D 4 is 1, D 0 is 1. So, what will be my output? So, will it be 0 0 0 or will it be corresponding to D 4 1 0 0? So, for the other input combinations where more than one inputs can become 1, there is some ambiguity. So, to remove this ambiguity, normally the encoders that we design, they are something called priority encoders, not a normal encoder like this truth table shows. Now, in a priority encoder, the input lines will have some priority, like suppose I have said D 0 I have applied 1, D 4 also I have applied 1, and I am saying that the line D 4 is having higher priority than D 0. So, if both of them are 1, D 4 will take priority and the output corresponding to D 4 will be generated 1 0 0. This is how the priority encoder should work. So, for a priority encoder, the basic concept is like this. Let me just repeat. Now, let us put it in the proper context. See, a priority encoder or means any encoder circuit, they are used in an application, let us say 4 inputs and 2 outputs. They are used in an application where some sub-circuits or some device or some units, they are generating some kind of requests. The input lines are assumed to represent unit that requests some service, and the output will indicate that which one of the inputs, that the input 0, 1, 2, 3, that are 4 input units, which of the inputs have generated the request. Now, in a priority encoder, as I said, whenever two of the inputs, let d I and d j, where I is greater than j, request service simultaneously, then you assume that d I is having higher priority, because I greater than j. So, the output will be generating the binary code for the highest priority input, that is active. This is how the priority encoder works. Okay. Let us look at the truth table, it will be clear. Think of an 8 by 3 priority encoder. There are 8 inputs, there are 3 outputs. For the first case, where only d 0 is 1, others are all zeros, there is no ambiguity, it is 0 0 0. But when d 1 is 1, d 1 has a higher priority than d 0. So, d 0 will be do not care, d 0 can be 0 or 1, does not matter, but d 1, but the rest are zeros, it will be 0 0 1. But when d 2 is 1, the lower priority ones will be do not care. It will only be important that the higher priority ones are 0 0 0. Similarly, d 3 is 1, lower priorities are all do not care. This is like this. So, the truth table will look like there will be lot of do not care entries here. So, when d 7 is 1, for example, so the other inputs does not influence the output. So, if d 7 is 1, the output will always be 1 1 1, irrespective of the other inputs, right. This is how a priority encoder works. That means, again I leave it as an exercise for you to find out how to generate the expressions. Just here I am showing out the expression for the outputs. So, for this f 2, f 1 and f 0, if you write down the expressions, then after minimization the expressions will be like this. So, I leave it as an exercise for you to verify again. So, if you want to implement these using gates, you will of course, first we will have to minimize this and then implement these using gates, right. So, f 2 for example, will require a single OR gate, nothing else is required. F 2 will require a single 4 input OR gate, 4, 5, 6, 7. This f 1 for example, will be requiring 2 AND gates, 3 inputs each. Well, of course, here some NOT gates also, some are bar are there, D 4, D 5 bar, and D 6, D 7 are direct. So, there will be an OR gate connect, D 6, D 7 will be direct. So, similarly F 0. Okay. Now, let us talk about a circuit element called comparator, which is also very important. Sometimes we need to compare the values or the magnitudes of two numbers, whether they are equal, whether one is greater than the other, or whether one is less than the other. This is called a magnitude comparator or a simple comparator, digital comparator. So, when you talk about an n bit comparator, it basically compares the magnitude of two n bit numbers a and b, and there will be 3 outputs GT, equal and less than, greater than, equal to, less than, where GT will be set to 1 if and only if A is greater than B in magnitude, EQ will be 1 if they are equal, LT will be 1 if A is less than B. This is how the comparator works, right. So, let us take a very simple scenario first, just a 1 bit comparator. So, I want to design a circuit where the two numbers are just single bit numbers A and B 1 bit number, and I have my 3 outputs greater than, less than and equal to. Now, obviously, A greater than B means what? For a single bit number, that A is 1 and B is 0, this is the only case. So, it will be A B bar, A B bar. Less than B means, so here also only one case, A 0, B 1. So, A bar B, A bar B, and equal case A equal to B, you see there can be 2 scenarios, A 0 B 0 or A 1 B 1. This can be expressed as A bar B bar or A B, which is nothing but the exclusive NOR function. Symbolically it is written like this, exclusive NOR. If A B are the inputs, output will be this echo. Because of this property, XNOR is basically checking equality of 2 bits. This is sometimes also known as the equivalence function or the equivalence gate. XNOR is sometimes also known as equivalence gate. Okay, 1 bit comparator is very easy to design. Let us look into larger size comparators. Let us say 2 bit comparator. Here I am assuming that the numbers are 2 bits, A1 A2 is one number, B1 B2 is another number, and I want to generate the 3 outputs. You see, let us construct the Carnot map, this A1 A2 along this side, B1 B2 along this side. Let us think of the 3 scenarios separately, greater than. So, what are the greater than scenarios? Let us take some examples, A1 A2 and B1 B2. Let us say when A1 A2 is, let us say 0 1 and B1 B2 is 0 0, then A is greater than B. So, when it is 1 0, B1 B2 is either 0 0 or 0 1, then also A is greater than B, and A1 A2 is 1 1, B1 B2 is either 0 0 or 0 1 or 1 0, then also it is greater. So, there are 6 possible scenarios. So, see in the truth table I am shown this as 6 possible cells where GT, GT, GT are marked, because GT, LT and EQ will be all exclusive, that is why I can show it on the same truth table. Equal to will be 0 0 equal to 0 0, 0 1 equal to 0 1, 1 1 equal to 1 1, 1 0 equal to 1 0, and the remaining cells will all be less than. So, directly from this single truth table you can actually write down the expression for all of them. Like for the GT, the cubes will be, one will be this, one will be this, and the other will be these 2. So, if you write down, it will be this. This EQ cannot be minimized any further, there will be 4 terms with all containing 4 literals. For LT also, you can combine this 4, you can combine this 2, you can combine this and this. So, there will be 3 terms, right. So, a 2 bit comparator is also relatively easy to design, you can do it in this way. Now, when we talk about a 4 bit comparator, let us see, suppose I want to design a 4 bit comparator. There are 2 4 bit numbers B0 to B3, A0 to A3, let us say. Let us denote or introduce a symbol called xi, which is the equivalence of ai and bi, that means XNOR function. That means, xi will be 1 if ai and bi are equal. Now, with this notation we can directly write down the expressions for EQ, GT and LT. You see A and B, they will be equal if all corresponding bits are equal, that means x3 is 1, x2 is 1, x1 is 1 and also x0 is 1, just AND of all 4. G3 you see, you think of the two numbers, the number A and B. So, if you see that A is 1, that A3 is 1 and B3 is 0, then you need not have to see the other bits, because irrespective of the other 3 bits, if the most significant bit A is greater than B, then always A will be greater, A3 B3 bar. But if you find they are equal, these two are equal 0 0 or 1 1, these two are equal, then you need to see the next bit, if this is 1 and this is 0. So, you see the first bit is equal and A2 is 1, B2 is 0, or the first two bits are equal, A1 is 1, B1 is 0, or the first 3 bits are equal, A1 is 0, B1, A0 is 1, B0 is 0. The LT is just the reverse, instead of A3 B3 bar is A3 bar B3, it is 0 1. They are equal and this, they are equal then this, they are equal then this. Same way you can straight away write down. So, you see for this kind of functional blocks, you did not always have to construct the truth table to write down the expression. You think mentally that what this block is supposed to do, and you can functionally you can write down the switching expression directly. This often we do for many of the functional blocks. So, with this we come to the end of this lecture on logic design. In our next lectures, we shall be looking at various ways of representing Boolean functions and some of the ways in which you can manipulate them. Thank you.